linear functions, we are going to explore the numeric, algebraic, and graphical forms of quadratic functions. Quadratic functions, you will recall, graph as a parabola. First, let's look at the numeric representation. You will recall when we studied linear functions that when there was a constant change in x associated with a constant change in y, and we'll look at that over here. This is up by 3's. Then the slope is 3 over 2. It's constant. There's a constant change in y with respect to x. That is how we knew that this table represented a linear relationship. Now when we go to the quadratic, it's a little bit different. Looking at the quadratic table, we can see it's going up by 1, up by 1, up by 1. So I'm not going to elaborate here. But over here, a linear would be ruled out because the change isn't constant. This one's going down by 9, and then these two are going down by 7, and these two are going down by 5. So that's obviously not linear. But let's check the difference between negative 9 and negative 7. That is plus 2. And going from negative 7 to negative 5 is also plus 2. And going from negative 5 to negative 3 is also plus 2. And negative 3 to negative 1 is plus 2. And negative 1 to 1 is plus 2. So the pattern is that the change in the change is consistent. We call that the second difference. Here is where you can stop the recording and try your hand at this. You can see this is going up by 1, and this table here is going up by 1s for the x values. Your job is to see if the change in the change is consistent. Did you get these differences between the y values? And then did you notice that between negative 7 and negative 5 we're going up 2? And between negative 5 and negative 3 we're going up 2. And negative 3 to negative 1 we're going up 2. And negative 1 to a positive 1 is up 2. And so forth. Did you get this pattern of differences? Between negative 1 and 2 there's 3. Between 2 and 3 there's 1. And between 3 and 2 it's actually going down by 1. And then 2 to negative 1 it's going down by 3. And then when you look at the second differences, we see this is minus 2. And this is minus 2. And this is minus 2. And so forth all the way down. This is the way we decide whether or not, by looking at the table, whether a function is quadratic. Let's look at the graphical representation of quadratic functions. You can see that the parabolas are in all different positions here. This one's actually flipped because of the negative in front of the x squared. But the point that I want to point out is called the vertex. Every parabola has a vertex. If the parabola opens up, the vertex is the minimum y value. We talk about functions having minimums and maximums. And when we do so, we're talking about how big can y get, or how small can y get. In this first parabola, the arms reach up for, well, up to infinity, and so there's no limit on how high the y values can get. But the y values will never get any lower than 0 on this particular parabola. So the minimum for this function is 0. On this one, you can see it's shifted away from the origin, and it's actually up 1. So the y values will never be less than 1. The minimum value for this function then is 1. And this function has a minimum, oh, wait, it's upside down. It goes down forever and ever. And so it has a maximum of the vertex, and the maximum value of this function is -3. So I'll write that down so you can compare. Here you can see I've written for this parabola, y is greater than or equal to 0. The minimum is 0. Here, y is greater than or equal to 1. The minimum is 1. Here, y is less than or equal to a -3. The maximum value for this function is -3. In this practice set, I encourage my students to enter the function in their calculator and explore the vertex. And I'm just using the calculator out of the book. So, on one. Here I've graphed x squared, and you can see I am tracing the point right there. The vertex is where I'm at. And if I trace up to the left, you can watch the y values here are growing. Y is getting bigger and bigger. Y is continuing to get bigger. As I go down towards the vertex, the y values get smaller, smaller, and smaller, but they never get smaller than 0. And then on this side, the y values begin to increase again. So we say that for this function, as you read it left to right, we read graphs, remember, left to right. Let's start over here. Watch the y. The y value is decreasing. The function is decreasing. The function is decreasing. The function is decreasing. Here, we have the minimum of the function, which is 0. Now our function starts increasing as we read left to right. The function is increasing because the y values are getting bigger. Here I've begun to record some of the information. The vertex is at 0, 0. The minimum for the function is 0 because y will never get less than 0. The domain are the x values that we could graph for this function, and any x could be plugged in here and get a sensible y out of it. So we would say all reals, or we could just write capital R. Kind of a pretty one, and everybody knows that means all real numbers. The range are the y values. Now there is no way you're going to get a y value down here. In fact, no y is less than 0. So we would write y is greater than or equal to 0. That would be the range. Here the vertex is at 2, 1. The minimum value is 1, and the domain is all real numbers for x, but the y values are always greater or equal to 1. And our last one looks similar, except in this case the maximum is -3. Instead of the minimum, you have a maximum. Now let's understand the algebraic representation of quadratic functions. The most basic we can get is y equals x squared. You might recall the little ditty, x squared, arms in the air, absolute value is a v, exponential next is power of x, half a smile, and your graph's complete. So x squared is the thing that makes a parabola a parabola. In standard form, we have y equals, and then we can have a number in front of the x squared, which we call a coefficient. We could also have another term, b, or any number, times x without the square, and we can have a constant, just a plain number. Anytime this coefficient on x squared is positive, greater than 0, the parabola opens up in kind of a smile. If a is less than 0 here, that means it's negative, the parabola opens down. Here are some examples of parabolas. Notice this form here we could distribute, and it would look similar to one of these others. So now's the time to practice. Can you arrange these functions so that you can see whether they will open up or down? In this case, we'd have to get rid of the 2 to get it in standard form, but does that really matter? No. You can see just by looking here that it is positive and opens up. In this case, though, to get y alone, we have to subtract the x squared from both sides. And when we subtract the x squared over here, you see the coefficient on x squared. When y is alone, your coefficient on x squared is negative. And so this parabola opens down. It's a complete rewrite here. On this one, we'd have to add the x squared to both sides to get y alone. And when we do that, you can see it is positive x squared. That's a plus. So rewriting, we would have y equals 4 plus x squared, or x squared plus 4. Let's write it in standard form. And yes, this will open up because the coefficient is 1, and it's positive. We need to look at domain and range for parabola. Now, for some reason, those words, domain and range, seem to really be difficult for students to remember, but if you can think of it as an XY table, the domain is anything you could enter for X, and the range is anything you can enter for Y. D for X and R for Y, alphabetical order. Domain and range, it ain't so strange, but it's just X and Y, how far left and how far right. Don't let that get you all uptight. And Y, how low, how high. Any of those things can help you remember. Y, in a parabola, the domain includes all real numbers, any parabola. And the range is going to vary depending on the shift of the parabola. Here, y is greater than 0. That's the range, or equal to. Y is less than or equal to negative 3, and here, y is greater than or equal to negative 1. And last, we are going to look at graphing a parabola. There are particular points that are more important than others. And we'll get into that more in future lessons. But for now, let's just remember how we played pick an x and then calculated for y. And our favorite x was always 0 because that gives us a y-intercept. So if x is 0, our y will be 2. And then let's try 1. Now y equals negative 1/4 of 1 squared. But 1 squared is just 1. So this is just 1. 1 times a fourth is negative 1/4 here. Plus 2. So then for x equals 1, we get y equals, if you have 2 and take away a fourth, this is 8/4. Take away 1/4. That's 7/4. A little less than 2. Let's see how that looks on our graph now. 0, 2, and 1, and almost 2. Looks like our parabola is going to either go up this way or down that way. So let's look at our equation. Here we see a negative. That means it's going to frown. So it's going to go this way. And we'll need a negative value to fill out the left side. So let's plug in a negative 1. But when you square a negative 1, negative 1 times a negative 1, that is a positive 1. So we have the same thing, negative 1/4 times 1. So we're going to get 7/4 again. So there's our symmetry. Parabola goes down that way somehow. Now, be aware that when you graph a parabola, I do expect to see 2 arms. let's go back over what was important about the quadratic functions. First of all, instead of being a constant change in y associated with a constant change in x, it's a constant change in x that corresponds with a constant change in the change in y. This is the change in y. It's not consistent, but the change in the change is consistent. The algebraic representation of a parabola requires that there be an x squared term, and the equation must be able to be written in this form. Now, this could be a 0. We don't necessarily have to have all this other stuff in there, but there does have to be at least the x squared. For a positive value in front of the x squared, the parabola opens up, and for a negative value, the parabola opens down. The graphical representation, we focused on the vertex, which is the minimum if the parabola is opening up. It is the maximum value for the function if it's opening down. Domain and range simply means all the x values and all the y values that are represented by the function. And then we went and reviewed how to graph. So now you should be ready to start your homework.